several research papers, book chapters, conference papers, and other articles in prestigious journals and prestigious conferences like IEEE Census, IEEE Nanoelectric Transactions on Nanoelectronics, and similar to that. He completed his PhD from IIT Delhi and MTech also from IIT Delhi with Electrical Engineering Department. He has completed his BTech from MNIT Jaipur, and he has been associated with the institute since last 3 decades. He has a lot of research projects to his credit at MNIT Jaipur, approximately 25 crore or more. He has supervised 14 plus PhD scholars and many of MTech and BTech students. Most of his students are placed at eminent institutes and big organizations like Intel, Apple, Google, IITs, professors at IITs and other worldwide institutions, not only in India. So, yes, it is over to you, sir.
Thank you, Menka. I hope I am audible.
Yes, sir, you are audible and slides are also visible, sir.
I am keeping my video off to use the bandwidth.
Yes, sir. Thank you, sir.
So, good morning, all of you, those who have been here for last many days. Today, my discussion will focus on something which is useful as a kind of a help to testing, and mostly it is to help the built-in self-test. The issue is we have to store the input patterns and output patterns. So if we are testing some circuit and placing your testing circuit along with your design on the same chip, right? DFT, basically DFT, design for test. So you have some part here. I'm not showing as a intermingled with design. It is intermingled with design. And we have a DFT there, design for test there. So what you need for design for test is the test application, test pattern application, right? And the checking the output, right? Check the output. So these test patterns which you need to apply should be available on chip itself. That's first requirement. So you need to have pattern stored pattern, right? If it is DFT. So you need to actually have the input test patterns available on the chip itself. Another requirement is you need to store the golden output. Golden output means fault-free output. Fault-free output, right? So these two need to be stored on chip, and hence there is a memory required for that, on chip memory. And this is a huge requirement actually, right? So we cannot do anything about test patterns. Only thing is, if we have exhaustive 2 to power n patterns, we use only very small fraction of it, right? So that way we reduce the memory storage to a small amount. About the golden output, we cannot do anything. For a golden output corresponding to this input pattern, I need the golden output pattern for each of those input pattern that way. Now the point is, if I store this sequence of output patterns, I need some storage. And because my input patterns are decided, number of input patterns, say 100 patterns. So I need 100 output sequences. I cannot reduce that. What can I do is, I can reduce the output width actually. Output width I can reduce, or I can compress the output. So my memory required is lesser that way. And that's where we are looking at test compression. The motivation is we need a large memory on chip for DFT or BIST, basically self-test. And we are looking for some help where I can actually have to store input patterns or generate automatically the alternate here, 1A and 1B. generate the input pattern automatically, right? So what we need for that part is uh, okay, I'm just trying to find out which way I have to do this. Uh, right. Okay. So we are looking for the test pattern generation or storing the input patterns. So part A is store pattern. B part is if you are applying some random patterns only, some 1% or something of total of whatever is exhaustive test pattern, we can generate that. If it is random pattern, we can generate the random patterns. Now this is extremely efficient because I do not need to store that and I can generate on the fly. So this circuit for generation of random numbers or random patterns should be on chip, and this is a little cheaper. And the second requirement for me was output pattern compression. Output pattern or golden output compressed form. I'm storing golden output in compressed form. Surprisingly, the solution to generate random pattern and a solution to generate compressed output and the storing of golden pattern, matching it with the current output, the circuit required is same. And that is called linear feedback shift register. There are various methods for compressing output and LFSR is only one of them. But it is widely used because it is also helpful in pattern generation. So our today's, you can say, target is to study the test compression methods, either for output compression first and later on how to generate the random patterns later. So first objective is the output test pattern check that way, right? Okay. So I am following one of that text, which is very old text, a very seminal text on testing, Abramovici. I will give you reference for that, but this is the basically the kind of requirement there. Fine. So various techniques for test compression, output test compression is this one, right? So the way we do it is, say you have the truth table kind of a thing for a given thing. Let us say for combinational test circuit, you will have your input vectors, which are, if it is n inputs, I0 to In minus 1. This is 2 to the power n patterns here. And then you have golden output, which for simplicity we can presume only one bit, O1 or O0, whatever you want to say. So we have only one bit pattern here. And the compression means when we have the kind of scan based application, and if I apply all these inputs, I will get this sequence generated. So what I will do, instead of storing 2 to the power n numbers, I will compress this pattern, which is 0, 1, 0, 1, 1, 0, 0, whatever. No, it's about 8 bits, n equal to 3. I will store it in a compressed form, maybe 1 bit, 2 bit, or something like that, right? So I will be compressing the output sequence. At least we are focusing on 1 bit output. So whatever sequence I get generated after application of all input patterns, which by the way is 1 bit output, I will just try to store that as compressed output may be in very small number of bits, 1 or 2 bits. You may say that because these are 8 patterns here, no? This is my golden pattern, and my faulty circuit will also have many other ways. So how many patterns I can have, output sequences I can have? Anybody? If I have n inputs here, my total number of input patterns would be 2 to power n. Then how many of these kind of sequences will be generated by either the correct circuit or the faulty circuits taken together? Yeah. How many such sequences would be there potentially? So I will be keeping this stored compressed form, and these patterns I will be compressing after testing. And the number of these patterns would be 2 to power 2n, the number of functions I can have. No? If this is my single function f input output relation, one output function, 1 bit output function for any given circuit under test, the kind of sequence I generate, the function I can realize will be 2 to power 2n. This is actually number of patterns sequence of output I can get, which is one of them is correct and others are all faulty. So you may say that out of so many functions, no, 2 to n, if I compress them to 1 bit only 0 or 1, most of them will actually have the aliasing. Many of them will bounce to 1, many of them will bounce to 0 or compress to 0. So 50% cases would be, they will all be same. The output compression form will be same. This is called aliasing, right? So the basic all fundamentals I have just conveyed to you. The rest of the slides are about, you can say, uh, the formal way of looking at these things, right? So what do we do is we have so many methods, right? Once count, transition count, parity check, and syndrome testing. And lastly, and not lastly, but one of them is linear feedback shift register, LFSR. We'll detail that out that way. So we'll quickly go through these 4 kind of compression methods, and we are looking for compression of output only, right? The output patterns only. And that also we are not compressing the output. We are presuming for a moment that our output is 1 bit only, right? Input could be n bits. And what I'm compressing is after possible application of sequences of outputs, inputs. So one of the sequence could be 0001. The last sequence could be 1111. So number of sequences I'm applying is 2 to power n exhaustively. So I will get the sequence of outputs, which are also 2 to power n. And I'm trying to compress this sequence because after my scan based testing, I will keep applying one of the patterns here, and I will get the sequence of output here in time domain. I will store them in a register and then compress it. So I'm not compressing the output pattern, I am compressing the output sequence. That's my main part here. And I will store my golden sequence of output in a compressed form. That's my promise. So this I will keep compressed form. On the fly, when I'm testing a circuit, I will get the output sequence, I will compress it, and then compare these two. So compressed circuit under test, pattern 1 and 2, I have golden compressed form, and I will compare them. So what I mean to say here is, I'm trying to compress output sequence, where I just presume for a moment for simplicity that output is only 1 bit, and I have sequence of 2 to the power n such outputs, right? Okay. So if I store my golden output signature, the golden output in a kind of a compressed form, I call it signature, right? I call it signature. The comparison of the above golden signature, we do it with kind of on the fly generated signatures. So a signature is a compressed form of output sequence, right? And then we do it on the fly. When we get a response sequence, the response is compacted. So they are all synonymous. The signature is a compressed form of the output sequence. Response compaction is corresponding to the same idea that we have a output sequence compacted, and so on and so forth. Right. So we look at the five kind of methods: ones count in the output sequence, transition count in the sequence, look at the parity, odd and even parity, or check for the syndrome, which is modified version of ones count, and finally the linear feedback shift register you use for signature analysis comparison also, right? Okay, we go ahead. So this is something which we had discussed earlier with my handwriting. This is only formalized in a slide form. So what we will be trying to do is we'll take this complete sequence and compress it. That's all. So these patterns are applied one at a time. So I will take the 2 to the power n steps in time and get the output sequences one at a time. Store that into a register, serial to parallel conversion or whatever you want to say, right? So we have output sequences stored here. One of them, 8-bit. Right? And I will try to compress it with a smaller number of bits, maybe 1 or 2. Right? That's the target. So if we have the n inputs, one output circuit, total number of test vectors would be 2 to the power n, right? And total functions we could realize will be 2 to the power 2n. Only one of them is a fault-free circuit, which is a golden one, right? So what we need is, I'm just repeating it on slide what we discussed earlier. So we need to generate the input vectors. We need to generate them, or you can have it stored on the chip, which is a huge memory requirement. It's a random pattern generation, much less than the 2 to the power n. The things are easy. Things are a little easy. If you want to find out what do we mean by one bit output only, if you take the n equal to 16 here, input number and 16, the total output sequences could be very many. Like we could have n16, and we'll have to apply total patterns 2 to the power n. The number of output which we could get one after the other would be this number. So we'll have a sequence of output 65,000 outputs. This is a huge number. There is a need to compress this, right, in a very small number of bits. That's the motivation for compression that way. Later on, instead of 1-bit output, we can extend it to here. We can extend it to multiple output, maybe 8-bit. So we'll get the 8-bit patterns and so many patterns, 65,000 patterns, because input is 16-bit. Total number of patterns we need to apply is 2 to the power n, 65,000. For each pattern, we will get the 8-bit output. 8-bit output for one pattern application. Second input pattern, second output. And we have 8 into this kind of a thing. So now we need to compress this number of bits, 8 into 65,000. So whatever we study for 1-bit output compression can be later on extended for AM output circuit, which we'll not discuss today. We'll discuss only for 1-bit output kind of a scenario that way, right? So this is the kind of a flow which we can follow, and we have input test sequence, whichever way you want to generate them, random or all test patterns. Then you have output here, output response sequence, one after the other, time wise. You're applying one pattern at a time. So T1, one pattern, T2, second pattern, so on and so forth. So you get the output pattern, and we presume it to be 1 bit only. So you have about many number of bits, 2 to the power n number of bits, 1 bits, and you compress it and generate a signature, which we call SR prime, which is response. We have a correct signature already, which is compacted, right? So we can say we have a golden output sequence, and we use the same compression unit, data compression unit, and generate this signature, and we compare, right? So our basic thing is this one, which we are looking for. Okay. So test compression is the requirement is it should be we should be able to implement it with a simpler circuit, and it should not reduce the extra signal delays in your DFT, and the signature length should be logarithm of the total output. It should at least be that. So what I mean to say here is, if you had 2 to the power n length of sequence, we should compress it at least into n length, which is log of this, right? So logarithmic factor means you have 2 to the power n sequence compress into at least n or less than n, right? That's a target that way, right? The main requirement is the signature of the faulty circuit and the fault-free circuit should be different. Otherwise, we cannot differentiate even our compression. If we lose the distinction, the compression job is actually a wrong way. After compression, we are not able to find out the circuit is faulty or not. So our fault-free circuit signature and the faulty circuit signature should be different after compression. After compression. So what we say, if it is faulty circuit has the same signature as the fault-free circuit, we say its error is masked. That error cannot be detected. It's a masking or aliasing. What does it mean is your faulty circuit has a signature R prime, and your fault-free circuit has a signature SR0, and by the way, they are same, right? Then we say error is masked. That error cannot be detected, right? It's the alias of the correct output response that way. So we'll try to find out fraction of all such possible erroneous responses and say that this is the probability of aliasing. Probability of aliasing. This means those signature which are same as golden, right? Number of SRs. Number of such SR prime signatures divided by total signatures, total number of signatures. The total number of signatures would be 2 to the power n for all patterns. So this will be 2 to the power n. And some numbers which are actually matching with the golden will be 2 to the power m. So our probability will be 2m minus n, where m will be much smaller than n. So this probability can be made very, very small, right? Looking at what number of bits we are choosing for compression that way. I will skip this for a moment and come back to the ones count. So how do we do that? The first way of compression, count the number of ones, that's all. Count the number of ones. So if you have a golden output of 8, say n equal to 3. So the inputs are 3 bit. we usually don't apply the 0, 0, 0, right? So how many patterns? 2 to the power n. I'll apply 7 patterns. 2 to the n minus 1. So my output length would be 7 bit. For a fault-free circuit, it could be 1001001. It is a golden signature, fault-free. For other sequences, they could be faulty circuits. Anything else. So varying from 0000001 to all 1111. This length is 2 to the power n minus 1. Right? So what we do to compress this golden, I just count number of ones present here, which is number of ones is 3. Number of ones here is 1. Number of ones here is 7. So I can go maximum up to 2 to the power n minus 1, 7. So I have so many numbers. 3 is my golden correct output, and I have 1, 2, 4, 5, 6, 7. They all correspond to the faulty signatures. Faulty signatures. And this is my golden signature. Right? So at least I have done this comparison very efficient. Earlier I had to compare 7 bits with golden signatures. Now I have to compare only 3 bits of golden. 3 I can store in 3 bits. No, 7 1. So I have to just compare 3 bits only to differentiate the golden signature or the signature under test with the golden signature. Right? That way. Fine. So we'll go ahead now. So this is the way we do it. Suppose we have a single output circuit C, right? And there is an output response, right? And we are applying few number of patterns, which may be, let us say, m number of patterns that way. So my output sequence would be of length m. So my output sequence is of length m, right? If I don't compress, I have a comparator requirement for a comparator for m bit. If I compress it by using ones count only, very simple, just count the number of ones. So this is the method, count number of ones only. So take only Ri, which is Ri is 1, when Ri is 1, right? The IC1R will vary from 0 to all the bits being 1, M. So I have a variation there. So if your M is 8, this ones count will vary from 0, 1, 2, up to 8, right? Or 7 in a way. Or 7 or 8 maybe. Yeah. So we have that ones counting. This is one of the way of compression that way. So what is probability for this is the circuit we are presuming. No, one output, one bit out only, one bit output only. So if we take an example of 3-bit input, then exhaustive patterns will be 8, number of 8. If n equal to 3, I would apply total 8 patterns. So this is first pattern 0 0 0. This is the sixth pattern. This is seventh, 8th pattern 1 1 1. So I'm applying all the patterns one by one at a time. So if I apply this first pattern, I will get the output as 0 for a fault-free circuit. This fault-free circuit output sequence. These two correspond to faulty circuit output sequence, right? If I apply the compression, the SR0 would be ones count. Ones count. What is the number of ones count here? The number of ones present here in this compression. 1. What is SR2? Number of ones present, 0. What is SR1? Number of ones present, 2. So looking at this, these are two of my computations on the fly for a faulty circuit. And golden circuit has this sequence. So number of ones present is 1. I can differentiate. If my number of bits which are changing here is 1 or more, then I can differentiate the golden signature with the faulty circuit signature, right? So we look at this, the compression. The compression is log of number of output sequences that way. So if we have 8 numbers here and my compression is the ceiling of whatever number of bits I'm having. So I may not apply the total exhaustive patterns, all 2 to the power n patterns. I may just apply m number of patterns which are less than 2 to the power n, right? So output sequence will be of length m, which is less than 2 to the power n, 8 in this case. If n is 3, 2 to the power n is 8, my m will be less than 8. Hence, the compression would be number of counting of ones, which can at maximum can be A7, 0 to 7, and I can represent them by 3 bits only. So this bit number of bits after compression, now how to represent them is through this value, log of whatever number of bits are there, number of sequence length is there, right? So there is a compression. There is a compression. Of course, there is aliasing. Actually, a huge number of aliases that way, right? If you want to just contemplate the aliasing here, how many such patterns would be there? This one correspond to the golden signature, fine. How many faulty signature could be there? Anybody? Maybe write in the chat. Somebody can help me reading chat. I cannot see chat in my presentation. How many such patterns could be there? Pankaj Nayak says 7.
Yes, sir, it is written 7, sir.
See, my golden output sequence is 8-bit, 8-bit sequence. The faulty sequence could be anything. So how many ways I can fill up the eight positions? Yeah. How many way I can fill up the 8 positions? This one is only golden. Rest of them, how many rest of them? The total numbers here. Is it not? 2 to the power 8 minus 1. I'm looking for these 8-bit patterns being filled up. Only one of them is the golden signature. Of course, I will have many such input, I think output sequences where there is only one, right? Only one. So all of these faulty sequences will have the same signatures. 7 such patterns. 7 such R prime, SR prime patterns will be almost same as SR0. This is my probability aliasing. So my faulty signature might not be differentiated in this case. 7 upon 2 to the power 8 minus 1. This is my probability of aliasing. These patterns, which are mostly 255 patterns, one of them is golden, rest of them are faulty, 255. Out of 255, I have 7 of them matching the golden signatures. That means those faults which generate these bit patterns, output patterns, cannot be differentiated, cannot be checked. Error masking is there, right? And what is this probability? 7 upon 255, right? Approximately about less than How much? 0.03 or something? Right. So probability is very small even with this once count comparison, right? And we never apply all stored patterns. We just have a random patterns, and hence this will still be going down. So the probability will be maximum this of aliasing, of wrongly taking the circuit to be correct where it is faulty. Did you get it? Right. So we have ambit sequence as we discussed. M here was 8 last time. No? For n equal to 3, input pattern length is 8-bit. Sai Kumar says why the output sequences are 255 and not 256. Because one of them is a golden signature, correct one. So we are counting the faulty ones. So faulty ones are 255 and correct one is 256. Right? So one of them is correct. So we are taking it as a 1 minus correct one. We are taking faulty signatures and how many of them are correctly identified. What I am saying is probability of aliasing. Sai Kumar, probability aliasing means how many faulty signatures are taken as a correct signatures. So how many faulty signatures are there? Out of 256, one is correct. So faulty signatures are 255 and 7 of them are matching with the correct one. Right? So these are called false positive. They are falsely characterized as correct circuits. Whereas we are looking at the total faulty circuits. So out of total faulty circuit are 255, 7 are classified as correct ones that way. So there's the probability aliasing. Is it okay, Sai Kumar? Right. So if you look at the kind of signatures having R number of bits, which is correct, compressed number. I am taking compressed number here is 1, but I say compressed number SR0. SR0 is small r. R number of bits are 1. Correct signature out of m bits. So out of total output sequence of length m, I have correct number of ones in correct pattern, number of ones are r. But the point is they are located at some place. Say 6 r's are there. I could fill this 6 r's some other way also. And their signature will be matching that. Right? So I can say that there are MCR numbers, sequences, which are actually matching the golden signature. MCR. I can fill up this M pattern with R number of ones in so many ways. Their signature, one's compression bit is same, R. Only one of them is correct. So rest of them are aliases. Right? Rest of them are aliases. So these aliases actually are wrong. Right? And how many total wrong circuits are there? Out of M patterns, only one pattern is correct. M bit patterns. So total patterns would be 2 to the power m, out of which only one is correct. Rest of them are faulty. 2 to the power m minus 1, these are faulty. Right? And alias are 2 MCR minus 1. So this is the probability of aliasing for R bits. For R bits. If you put R equal to 1, you get the same number we got in the previous slide. If R is more, you get some different number that way. Right? So this probability of aliasing, what's the distribution? Probability of aliasing, this distribution. If I take R varying from 1 to up to m, the probability of aliasing is MCR minus 1. How it is distributed? Binomial. How is a binomial distributed? It is peak at m by 2 and a very small number at this, and a mirror symmetry. Whatever I draw here, I will draw here. Whatever I draw here, I will have to draw here. And this is almost binomially distributed. Continuous way, Gaussian, matching Gaussian in a continuous way. So when you have m to be m by 2, if your signature is approximately m by 2, your probability aliasing is maximum. And if your signature, compressed signature is either number of ones are very high or very small, probability is very small. That we have to keep in mind. Right? Fine. If you understood this, we can go ahead very quickly now. This is what we have. So this is what we have just encountered. No probability of aliasing with ones counting. So we can keep computing probability aliasing, which is number of faulty signature taken as correct divided by total number of faulty signatures after compression. This is the false positive we are trying to do. And we'll find out this value for all other methods also. Right? So this could be just simple way of implementing. So for your DFT, you need nothing, just simple counter you can put on your chip, right? As a on chip DFT. You just need to put this counter, which is a compressor. That's all, nothing else, right? So it will keep counting the number of ones here. This will take about m number of clock cycles to compress. Output will be there. You may have combinational counter. We'll discuss it sometime other else, right? Which makes use of priority encoder. Priority encoder. You can use priority encoder to realize combinational counter. We'll discuss some other time, not today. So this is a very simple circuit for compression, very well implemented. So this is a good method of compression. So this is just analysis of one's compression, what can happen. So probability is, probability is approaching very high when your midpoint is there. So number of ones which are half of your bit length, then probability of aliasing is too large, right? What can we do else? What else can we do? We can look at, we are counting number of ones. Let us say golden signature. R0 is there. So R0, we might take 8-bit, 10, 11, 00, 11. This is okay, right? So my SR0 would be number of 5 number of that way. Now my alias sequence would be same, 110, right? And 1011. The SR signature for this will also be 5. So one's count cannot detect this aliasing. But if we take for each bit change, I convert it to a waveform. Right? And I count the edges, rising edge and falling edges. These will be different now, because if I get all 5 numbers together, the rest of 3 zeros this way, there's also another kind of faulty sequence with the same signature, 5. But the number of transitions here are 2 less. So number of rising edges and falling edges are 2 only here. The incorrect signature, how many edges are there? One is this rising, falling, rising, falling, rising, falling. How many edges? Transitions? 6, right? One is this, second, third, fourth, fifth, and sixth. Here, this one, 2, 3, 4, 5, 6. By the way, 6. So this may not serve the purpose. But for this, the number of count is only 2. Transition count is only 2. So out of what we could not differentiate in one's count, we are able to differentiate in transition count. Many of them are thrown out. So probability of aliasing in transition count is much smaller than the ones count, right? So this is a little improved version of that card, right? So transition count is, the way we do it is the bit change. The bit change, we take it as XOR, no? The kind of, you do it with your, I think some coding. No? So if you have the tests, the output sequence here this way, you keep doing XOR between every adjacent bits to find out whether there's an edge. So any XOR between 2 bits resulting into 1 will be an edge, rising or falling, whatever. Any one of them, at least one of them, rising or falling. And this is the way to transition count. The probability of aliasing with transition count will be less than one's count, right? So what is the maximum transitions we could get is every alternate bit we have, no? So the number of count rising has is, falling is here. So we have 1, 2, 3, 4, 5, 6, 7, 8. So number of count could be 7. Number of transition could be 7, right? Maximum number 0 to 7. 0 may not count because you never apply all zeros as a test pattern, usually that way, right? And we have that aliasing probability computed that way. So now I have initiated you with some understanding of mine conveyed to you. This still is a same way, right? So we just prepend counter with the transition detector and feed that as a bit to counter. It will count the transitions here. So a small modification can give this, and transition detector could be just flip-flop, right? If every transition, it will give you 1 bit kind of thing. Or just a simple detector you can design on your own way, that way. So this could be a simple transition detector, which is a D flip-flop along with XOR gate. So what we are saying is this circuit, which is here, I'm sorry, this circuit which is here could be realized with this one, right? A flip-flop and a XOR gate. So whenever there is a change here from 0 to 1, that 0 will be stored here, 1 will be applied here, right? And we'll get 1 output here. If there is a 1 to 0 transition, 1 will be stored here, 0 will be applied here, and we still get another one. So the circuit will very well detect the edges that way, right? So we can just do the analysis for transition count also, and the probability of aliasing would be this one, right? Twice of m minus 1 CR divided by 2m minus 1, right? You can just do analysis that way. Our main target today is the LFSR, linear feedback shift registers, that way, right? So before starting that, I should complete that part. From transition count, we can go to parity check. Parity check is very easy. You just take odd parity or even parity, and you just get it. That's all, right? So you have to keep counting. what do you get, right? So this is a serial ladder kind of a thing, right? This is a kind of a serial ladder, 1-bit serial ladder. This will modulo 2 adder. There is no carry. So this will just keep adding till you get the last bit in, and will give you the parity output. The sum is 1 or sum is 0. Sum will be 1 if your odd number of ones are there in the sequence, and sum will be 0 if you have even number of ones here, right? Very simple circuit. And this will compress your faulty or fault-free circuits into two parity only, 0 or 1. So aliasing probability is almost 50% or more than that. More than that. But this is one of the way. This is one of the way. Syndrome testing is almost like once counting, but we just take the ratio. We take the ratio of one's count along with how many number of bit positions are there. So total number of min terms available. So if you have n bit function, total number of min terms would be 2 to the power n, right? And I will count how many number of ones are there in a function. So if you look at this very simple way of looking at it, we'll count the number of ones in the function definition, number of ones in a function's definition, and total number of min terms. Total number of min terms will always be 2 to the power n, right? This will be called syndrome. So if you get any gate, let us say AND gate, 2-bit AND gate, no? This is the function, 0, 0, 0, 1. This is the function. In this function, how many ones I have? Only one. So syndrome for AND gate for 2 input is only 1 in that function, and total number of min terms are 4, right? So this is number of ones in the function, and this is your syndrome. So we define syndrome like this, right? For AND gate, syndrome is different. For OR gate, syndrome is different. For OR gate, the function would be 0, 1, 1, 1. So it has 3 ones, and total number of min terms are 2 to the power 4, 2 to the power 2, n. So this is 3 by 4. So for OR gate, the syndrome is 3 by 4. For AND gate, syndrome is 1 by 4. And similarly, you can count syndrome for XOR gate. It is 2 by 4, right? So how do you take the syndrome of the compact circuit? The circuit is made up of AND OR and XOR gate, no? And for NOT gate also we can find out the syndrome. 0, 1, it is 1, 0. It is 1 by 2, equal to the XOR gate syndrome, right? So if circuit is made up of these gates, we can count the compact syndrome of a circuit because circuit is made up of these gates that way, right? So this says that for an input combinational circuit, let us keep in mind, there is a n bit combination circuit. This could be 1-bit output. There would be 2 to the power n test vectors or 2 to the power n min terms. Each test vector is 1 min term. Each test vector is 1 min term, isn't it? Fine. So the syndrome would be how many number of ones are there at the output for the complete function applied. For 2 to the power n test vectors, what is the function? We realize. So we have 2 to the power n vectors here, and we have a function here, right? So for this function here, how many number of ones are there? I say k number of ones are there. Our function uses k min terms. Function f has k min terms only, right? So k number of ones are there. So then function syndrome would be k by 2n. That's all. That's what we say. Right? So if you look at it, for 3 input AND gate, the syndrome is 1 by 8. But for 3 input OR gate, syndrome is 7 by 8. Right? Fine. For a complex circuit, to compute the syndrome, let us compute the syndrome of C. Given that S1 for C1 is known and S2 for C2 is known. So C1 could be a simple gate, you can say. C1 could be a simple gate for to start with, and or not, or maybe your universal gates also. So C1, C2 could be chosen from any one of these gates for which syndrome S1 is known. Now to compute syndrome for C, S3, what do you need? You need to find out when C is 1, right? There is a function f for C1, there is a g function for C2. If S1 is a syndrome where we can say K1 ones are there, what do you mean by that? The input is n bit, total number of minterms will be 2 to the power n. There are K1 number of ones in function f. That simply means that function f, if I look at the function f truth table, function f has only ones at K1 number of places. So only K1 number of minterms are used for f. Whereas for G, K2 number of minterms are used. Right? To find out, K3 is to find out if C is OR gate, let us say. The C is OR gate, let us say. If your C is OR gate, when will be this output 1? If C is OR gate. Whenever either F is 1 or G is 1. Fine. When F is 1, it doesn't care whether G is 1 or not. So that means all 2 to the power n minterms of G, or if you have input different, you can say n1, n2. So for all 2 to the power n minterms here, whenever f is 1 in how many number of times? K1 number of times. F is 1, K1 number of times. With each of that 1 in f, we can have G having any value. Still then, we'll get 1 here. If f is 1 here and G is of any value, any don't care value, my OR output will be 1. That's what I'm counting here. First time. Second time, if my G is 1, whatever way, my f can be any value. Still the output will be 1. That value is G2, 1 would be K2 number of times, and f is don't care, 2 to the power n1. Right? Only thing is, in this and in this, we have counted when f1 was K1 and G was K2. These are counted 2 number of times. Right? I come back with a little more diligent way of doing this. Understanding this, little more diligent way. I write this again. K2 into 2 to the power n1 is your f being 1 or any value. F1 will be K1 times 1 and rest of the time it will be 0. So F1 is K1 number of times 1 and rest of the times, which is 2 and 1 minus K1, will be 0. I rewrite this again. K1, F1 is 1. and G. G is K2 times 1 and rest of the point 0. So number of times it is 0 is 2 into K2. If you add these two and look at this, you find out that K1, K2 is multiplied here and K1, K2 is multiplied here 2 times. So we must subtract this 1 time. That's all. And I have got the K3. This is K3. Now, right? So I write K3 here. Top K3 equal to K1 times 2 to power n2 plus K2 times 2 to power n1 minus K1, K2. Right? So what is syndrome now? Syndrome is K3 divided by how many number of minterms are here. So these total inputs could be n3, whatever, or total number of whatever you can get that way. So this will be total number of in the this way. If I take this complete circuit now, so my total number of minterms will be n1, n2 combined, 2 to power n1 plus n2. Right? I write it with a different color so that it is visible. I'm trying to write the syndrome for this. So syndrome for this is K3 divided by total number of minterms. So if I take this complete circuit, and this is, I'm sorry, this complete circuit, and I'm trying to find out the syndrome for this S3. So K3 number of times it is 1. How many minterms are there for this circuit? Total number of inputs. How many? Total number of n1, n2. And total minterms will be 2 to power n1, n2. This is my syndrome now. If you expand this, you'll get the answer for S3 in terms of S1, S2.
Excuse me, sir. If you
अभी
put,
दो
we
मिनट
can
दो मिनट पूरा कर देता हूँ मैं 2 मिनट पूरा कर देता हूँ.
Yes, sir.
Just 5 minutes. We'll take a break, sure. So this could be the syndrome for OR gate, AND gate, taken the way we have done it just earlier. We'll come back to this little later. We'll go it here. So my syndrome would be this one. K3 would be K1 to N2 this way. If I divide it by this value, my S3 would be, see, divide this by this. So these 2 to the power will go away and I'll get this pattern. So this is S1, this is S2, and this is my K1, K2. The gate I have observed was OR gate, if you remember, OR gate. So this is the syndrome for OR gate. Similar thing, you can apply the same circuit where C you can take as AND gate and compute this kind of syndrome for AND gate again, right? That will be S1, S2. You can prove that. So this is syndrome for OR gate, syndrome for AND gate, and so on and so forth. Right? So we have this one. This is the syndrome when we have no input sharing for OR gate, for AND gate, for NAND gate. NAND gate is just inverse of the AND gate. NOR is just inverse of the OR gate. And XOR gate is almost same as OR gate, with two terms being out. So you can find out for XOR gate. So you can take it as an assignment for your part that you show. See, if you are taking all quizzes and assignments, your performance will be counted. If you haven't done very good in the quiz or whatever, you must do the assignment. The assignment is prove this. The syndrome for XOR is this. Prove this. Just do it on a paper pencil way. Scan it, upload to drive, and put the link into your canvas. The assignment will be floated for you. Right? So I'm just coming to the start of the LFSR, and we take a break, small break that way. So this syndrome testing, and we know that what is good for syndrome is it is better among all the four: ones count, transition count, parity count, and the syndrome. The best way to know about this is the redundant circuit without common inputs, right? What is common input is fan out. We'll see deconversion fan out. I will tell you. So till now we have presumed N1, N2 are mutually exclusive. Inputs N1, N2 are mutually exclusive. In that redundant circuit, if we realize a function which is unit function, then all its variables are syndrome testable. Excellent. If your function is unit function, right? If your function is unit function in all variables, the function is syndrome testable. There is no aliasing. Very good. So if you realize that your circuit under test is a function, combination function, which is unit function in all variables, then it's good. The unit function is, for example, unit function is A plus B bar C. Here A appears only in one form, positive form. B appears only in negative form, and C appears in positive form only. Whereas F2 A bar B plus ABC bar plus B bar C is not unit in any variable, because A bar is appearing here and A is appearing here. B is appearing here, B bar is here. C bar is there, C is there. So this F2 is not unit in any function, whereas this F1 is unit in all three functions, all three variables. This function is syndrome testable without aliasing. That's a very good result. Excellent result for us, right? Very good result for us. So you can look at those lemmas and look at the book and read all those kind of things. Now we'll shift to the signature analysis using linear feedback shift register. Linear feedback shift register, LFSR, which we stated earlier, can be used not only for compression of your output, but can also be used for random input pattern generation. We are looking at this firstly for compression, output test compression, output compression, the very first application. But the second is it could be used for input pattern generation, random pattern generation. Let us come back after a break of 5 minutes. We'll start again. Thank you.
Thank you, sir. So let us have a break of 5 minutes and then we will be back. Thank you. Yes, sir. Can we start, sir? Hello? Hello? Am I audible? Hello, sir. Can we start it now? Hello? Sir, can you hear me? Hello? Hello?
I can hear you. We can start now.
Okay,
Sure.
sir. Thank you, sir.
Right. So I think I have a little less of a time. So I will just focus on, let us come back to the compression. 4 techniques we have done. Now we are looking for linear feedback shift register, right? Linear feedback shift register kind of a environment. So let us first look at what this means, what are the components, and then we'll do the analysis. The analysis would be, uh, let us say, what is circuit of LFSR, supposedly. Then we'll just look at how can we design LFSR, right? And then how can we use it for signature analysis, like compression or random pattern generation, right? So it's a linear feedback shift register. So there would be a register, right? So a single bit register would be this, where it could be D flip flop. Do you agree? And we'll have a input coming to it and output going out of it, because it's a kind of a register where we can take the parallel out also, but there is a provision for serial in, serial out. Serial in, serial out. Now, what is linear about it is the addition and multiplication of some signals, right? These signals is linear. When it is linear, if you go for, let us say, modulo 2 operations. The modulo 2 addition is what? XOR. Fine. And modulo 2 multiplication. Modulo 2 multiplication. Let us say I have to multiply 2 bits. A and B, both are 1 bit. What do you mean by modulo 2 multiplication? Modulo 2 multiplication. We will not extend it, it's just 1 bit output only. Modulo 2 means we have only 2 numbers to represent the whole system, that's all. So whatever you add and whatever multiply, the output or the result cannot be else than 0 or 1, nothing else. Modulo 2, that's all, right? So 0, 0 multiplication is 0, 0, 0, and this is 1. If I say that I have a signal here S getting multiplied by some constant Ci, Si multiplied by Ci. So this could be Si, this could be Ci. So what do you mean by multiplication here now? Can somebody indicate? C1, Ci could be 0 or 1 and S is getting multiplied. So if S gets multiplied by 0, what do you mean? What do you mean by that? We could take this is Ci, let us say, and this is Si. So if you have C not present 0, what do you get output? 0. If Ci is present, then your signal is repeated. So if Ci is 0, nothing is there. If Ci is 1, Si comes in. In this case of multiplication, the Ci is working as a switch. Multiplication, the Ci is working as a switch. If Ci is 0, that means switch is off. And if Ci is 1, switch is on. That's all. Right? So for addition, I can take the XOR gate. For multiplication, I can take a tap and multiply it with Ci. And there is a feedback. So that means I can take tap from previous tap and feed it to the present one. Something like this. So this could be 1-bit shift register with feedback, which is linear. This could be 1-bit shift register with linear feedback. So we have done the circuit contemplation. What could be there? It could be n-bit LFSR. How to design it is the main thing. Application is very easy. Let's take the step for design. Right? To be able to realize and design and implement the LFSR, we must first know on what basis we are gathering it. That's called characteristic polynomial. Characteristic polynomial. There could be two types of LFSR. And if you take LFSR as some kind of a sequential circuit, we could draw an FSM for this. Any FSM you draw is always periodic. If it is n-bit coded FSM, we represent one state vector as n-bit. For 3 bits, how many states I can have maximum? Number of states, k, 2 to power n. And if I go through the whole FSM, how many states I can get through singularly before repeating them? This number only, 2 to power n. So period of FSM will always be less than total number of states contained in FSM. Usually. Right? So, or it could be even larger if you have some kind of periodicity that way. But it will definitely be a kind of much smaller number than 2n factorial. 2n factorial is the way you can have the sequences, right? So if you have m length sequence, let us leave it apart. You have m length sequence of 0, 1, 0, 1. How many such sequences I can have, or distinction I can have? No? So that will be like I can fill it up with some numbers, 2 to the power m. Now I have these as sequences varying from 0, 0, 0, 0 to 1, 1, 1, 1. I can take these patterns in any sequence. First 0, 0, 0, 0, 0, then gray sequence or number sequence or many sequence. How many such sequences are there? So I can find out the sequence. Sequence number 1. I can fill with any one of the patterns out of 2 to the power m. Second place, I can feed it with 2 to the power m minus 1. Rest of the patterns and so on and so forth up to 1. And they are all permitted. Right? So the total sequences I can realize by m bit number is 2 to the power m factorial, a huge number, right? But that will be periodic. FSM will be periodic, definitely. It cannot have an infinite period, right? This is very important from the point of view of random numbers. Ideal random numbers will not have any period. They will not be repeated at all. But in our case, if we use LFSR for random number generation, it will have a periodicity. It will repeat after some time. That's why they are called pseudo-random numbers. One more characteristic also. So we have discussed something here that we have to design the LFSR. It has a period. Then we can correlate that with a polynomial. Very fantastic correlation. If you have modulo 2 arithmetic and you have a polynomial in x, power of x, then we have a perfect matching with bit patterns and a polynomial. What I'm saying is, a polynomial will have a perfect matching equivalence with bit pattern of same width, m bit pattern. We can represent m bit pattern by a polynomial, and whatever operation we do with between patterns, we can actually do those operations with polynomial. That's the beauty about the polynomial algebra, which is Galois field algebra, modulo 2 algebra. It has a perfect correlation with bit patterns of modulo 2 arithmetic. Right? Fine. Nothing complex here, very simple way. I just tried to define there is an equivalence between polynomial and a bit pattern. That's all. And we just saw the modulo 2 kind of any shift register relation will have equivalence with n bit FSM and will have a definite period. That's all. Two things. That's all. Nothing else. So the way we can realize the LFSR, linear feedback shift register, is two types. We'll see that. We'll see that. The one type was we just saw a D flip flop with a XOR gate with a feedback, right? So if I have multiple of these D, there could be a single output which can feed all of them. This is one to many. Single output feeds every feed at the backside, one to many. So one output, one tap feeds many, one to many. Or there could be another kind of feedback where I gather output of every flip flop and combine this all outputs in XOR gate and take single feedback. This is many to one. That's what we define as type 1, type 2. The circuit configurations, that's all, nothing else. Do you follow me? So type 1 is many to one and type 2 is one to many, right? One of them. We'll see that. So this you should keep in mind. We are reading LFSR, right? From the point of view of two major applications. The first application which we wanted was the signature compaction. So this is there. And the another application which is very prominent and very useful is random number or random pattern generation, you can say. Random pattern generation. Number is binary bit sequence. This number is equivalent to binary bit pattern. Binary bit pattern. right? Fine. So let's have some examples before we gather the generic circuit of LFSR. Let's take some examples. So this is a very simple example of a feedback, right? There is a output here is fed to the main input here. That's all, nothing else. And we have input some way stored there. So this is called the initial state, right? This is called initial state that way. So given initial state, how many other states we can go through that we can find out this circuit configuration. So let us take this example as a given circuit configuration, analyze it. So if I store any non-zero pattern, let us not store 0, 0, 0, because all zeros, when we do some arithmetic multiplication, addition with modulo 2, right? Modulo 2 arithmetic there, the 0 zeros will always result of 0 zeros. So keep in mind the LFSR will never have the initial pattern as 0, 0, 0, 0. It is forbidden because our modulo 2 arithmetic will result into always all zeros if the initial pattern is 0, 0. So this is altogether avoided, never used as an initial pattern. So initial pattern can be anything else. So it could be 1, 0, 0, 1 or 1, 1. So if we have initial pattern as 1, 0 here, what will happen? One clock further, these two are D flip-flops. One clock further, this 0 will shift here, this 1 will shift here. So next one is this one, pattern 0, 1. Next clock will come back to the same initial state, right? So we have two states only. The periodicity is two states or two clocks. So period is 2. The period of this FSM or LFSR is 2 states, 2 clocks, 2 states, whatever. So this has an answer for this also. If initial state is 1, 0, these two states can be alternately reached every time. Even if we start with 0, 1, same states will be there. So if S0 is 0, 1, S1 will be 1, 0. And it will keep going into the same loop and period there. If it is 1, 1, S0 is 1, 1, 1, S1 will also be 1, 1. So period is 1 only. It is stuck up in one state, right? So this circuit is good enough only for initial states of 0, 1 or 1, 0, right? This is the analysis of this, right? The period is 2, right? Period is 2. The maximum period could have been 2 to the power n, 4 factorial, whatever. We don't know. We were not able to reach that. At least 4 could be there, but we are not able to reach that, right? Till less than that. Another example, using addition, modulo 2 addition. So these are XOR gates. These are XOR gates. And this is a feedback. So this feedback is given from everybody else, everybody. And we take one output only. So this is many to one. Many to one. Right? So this could be type 1 possibly. So if we have 1, 1, 1 as input, then what would be the next state? So this 1 will appear here, this 1 will appear here, 0 is here. The 0 with this 1 will be 1 here. We'll get 1 here. So next state will also be 1, 1, 1. And this is stuck up in this only. So only length we can cover is only length 1. Right? If we have the same example but with different input, 0, 0, 0 is forbidden. And now we see that 1, 1, 1 also is very bad. So we take any other inputs, any other patterns as initial state. So with the same circuit, if I have another initial pattern which is 0 1 1, right? Then what do I get? Next state could be 0 0 1, then 1 0 0, 1 1 0, and we come back to 0 0 1. So period is 4. I go back and look at this output, which is output of the last flip-flop. Output of last flip-flop. If I look at that, right, in this scenario, if I look at that, this is first one, right? This is 1, 0 0, right? So 1 1 0 0 is my output. Looking at that, if I go ahead, this will be repeated, nothing else. So I'm repeating. This is my sequence. I'm repeating it again with the same period. So period is 4, and I'm repeating the sequence. Pattern stored in the registers, or my output sequence is repeated. So we take this output sequence as our indicator for period, right? And we have this as 4 here, right? Another circuit with a little less kind of a thing. It is one more uh, XOR is lacking, but surprisingly, its length is increased. So I go back. It has 2 taps here. For 3-stage LFSR, it has 2 taps. For 3-stage LFSR, it has only 1 tap. So number of taps matter. And here with number of 1 tap, we are able to realize the largest length sequence, period 6, right? Period 6, repeated otherwise. No. Repeated otherwise. Right? So this sequence is repeated after every 6. Period is 6, and this is maximal length possibly 6 or 7, right? 6 7 7. Initial state is 0 0 0 0 1 1. So length is 7, and 7 length is maximal length. 2 to the power n length will never come. It is maximal length. So there are special LFSR which can be realized which can have the maximal length period. That's very good, and we should learn which LFSR lead to maximal length sequence so that period of repetition is maximum. That's all, right? That's all the target is. Very short target for few slides that we are looking for LFSR with maximal length sequence. How to design that? Before design, we analyze. How to analyze? Before analysis, let's go through the kind of arithmetic. So you have modulo 2 operations, right? So linear circuit is modulo 2 operations. It has only one feedback, one D flip flop. For delay is sequential 1. You have only adders, which are modulo 2 adders. You have multipliers, which are modulo 2 multipliers. Fine. The delay we can translate to that kind of a polynomial. So we take x as an indicative of one delay, right? So x doesn't matter actually for addition multiplication. Usually it doesn't matter, but that is a polynomial element variable that way. Now for implementing adder, 2-bit adder, let's have a look at this table. So if I have 2 bits here, each can take either 0 or 1, 0 or 1. So this is my output, addition. Naturally, this is XOR gate, right? This is XOR gate. For multiplication, if each bit can be 0 1 0 1, this is my output. It says that the output is only 1 when both of them are 1, right? It could be ending, you can say. So ending is nothing but a switch. If one of them is a kind of a control variable, it's a control, then AND gate becomes a switch. Whenever control is 0, this input is not connected to output. And whenever control is 1, the input is connected to the output. Right? So multiplication is nothing but a kind of a switch. And that multiplication will be indicating by a circle Ci. Ci is a multiplier. So this control value which was saying could be Ci multiplier. Right? More arithmetic. If I add two numbers, two kind of variables in modulo 2, they add up to 0. If I take these as variables, no, this is x1, x2, whatever. So I add two variables, that means same value, same value. So same value addition is 0 always, XOR gate. The XOR gate output is 1 only when the bits are different, right? Multiplication of 2 is same bit, that way. Any number powered, any number, this will be remain the same number. So this is synonymous there. It will be 0. Modulo 2 addition and modulo 2 subtraction are same. They have no difference, right? So keep in mind this way, this thing. So these two types we could have. If you realize the first one, the first circuit, this one, we have taps from many places, and we gather it for one output only. So this could be taken up as a single OR, multiple input OR. Multiple input OR. Or these each of them is a 2 input OR. Right? This is type 1 LFSR. If you look at this, we are taking tap from the last one and deriving tap for everybody out of that. This is same for everybody. We are deriving tap for everybody, and then having XOR from previous one, current value and the previous one, or the present one. Right? The C1, C2 are multipliers, but C1, C2 are all modulo 2 numbers. So it is a kind of a switch. Ci connects input to output or doesn't connect, depending on whether it's a 0 or 1. That's all. So these C1, C2, Cn are nothing but switches, or not switches. If they are connections, so C1, Ci to be 0 means no connection, and Ci to be 1 means a connection. That's all, nothing else. In a generic form. We analyze this in detail, quickly, in 10 minutes, and then see the signature analysis. Right? Many to 1, type 1. Many to 1, type 1. What are we doing? We are labeling them as the first flip-flop and first multiplier out of that flip-flop, second flip-flop and a multiplier of the second Cn. And hence, the Cn is always 1, because if you don't take this feedback, you're lost. No? So Cn has to be definitely 1. There is no other way. We are labeling this flip-flop as 1, 2, 3, n length. We are also labeling these taps actually. This is x to the power 0, x square, xn here, xn minus 1 here. Right? Just remember this. Let's go ahead. Repetition. Sorry. So what we look at this LFSR is my digital circuit. I try to correlate with this polynomial, some polynomial, so that whatever I want to do in digital circuit, I can parallel way illustrate it by doing some operation in polynomials. That's all. Each LFSR will have its signature polynomial, a unique polynomial for it, which is called characteristic polynomial. Let us derive that. Right? Now, if I take output of any flip-flop here, see serial output. I need to represent this output bit pattern also as a polynomial. So I will say, I will place them at some delayed kind of a thing. They are time delayed, no? Time delayed. So first one I take as MSB. So this could be one. I say this is delayed in, this could be X. This could be X square. It's absent. So this is X4 present, X6 present, and so on and so forth. If these are delay elements, even if I put some summation in between them, it doesn't matter. So this sequence I can represent it by 1 plus X, X4, X6, like that. Right? Time delayed, because this is a serial sequence. This polynomial will now represent this sequence. Right? This is called generating polynomial. Generating polynomial. Right? Any GX. This can represent any bit pattern. Any bit pattern. The first one is A0, MSB. The LSB is there. It could be infinite bit pattern that way. Right? So these A1, A2, A3, AN, AM, they're all coming from modulo 2. They will only be 0, 1. So bit pattern. A1 to AM is bit pattern, and GX is the polynomial corresponding to that. Do you understand now? I go back. By this pattern, I'm sorry. By this bit pattern here, I'm sorry. By this bit pattern has a corresponding polynomial here. That's what I'm saying here. My this bit pattern has a polynomial here. That's all, nothing else. Do you follow? Very simple. So now let's characterize this LFSR with some polynomial. For LFSR, what we did earlier was we have a bit pattern and we have a polynomial. Fine. For this LFSR could be represented by a typical polynomial, which is characteristic polynomial. Right? Right? So in that case, we have to do some kind of a tagging. So the tagging is the flip-flops. We labeled this as 1, 2, 3, 4. So same way, this is the output, Q1, Q2, Qn. The Qn is tabbed and applied to everybody. Hence, Cn is always 1. Fine. C1, C2, Cn minus 1 could be anything, 0 or 1, flexible. What I'm also doing here is, I am saying this initial pattern is there. If I have initial pattern stored here, then I have something. So we say it's the initial sequence, right? So this is A0 and this is delayed. So I'm taking time delay. So labeling them as minus coefficient that way. Doesn't matter, just a labeling. At any other point of time, there will be some other sequence at some time, which I can say this is AM, hence this is AM minus 1, and this is M minus N. That's all. I'm referring to values or taps here if I'm doing these here. Is that okay? Here itself we know that this A minus 1 is nothing but delayed A0. No? A minus 1 at time t is equal to A0 one previous time, one step before. Do you follow? Do you follow? Just relation between flip-flop. There is no addition and subtraction. So if I take somewhere here, right? Suppose AM minus I. At time t, AM minus I at time t here will be related to this pedacer through flip-flop, right? So AM minus I minus 1 pedacer delayed, one coefficient delayed. like this, right? So I take this for simplicity. A1 is delayed version of A0. Because my delay is represented by X, one delay, I can transform this and say that it is X multiplied by A0. X multiplied by 0, because both are indicative of delay. So X A0 means A0 divided by X. So can I write here that if this is 1, can I write X here divided by 1? Can I write X square here? Can I write X cube here? Can I write Xn here? Do you follow me? If you understand this, complete. The analysis is complete. Things are done. We just have 2 more slides to characterize this. That's all. Have you properly labeled it? Any queries? These 2 expressions are just indicative.
Dear participants, if you have any query, you may type in the chat box. We will take it from there. Sir, there is some query. What is modulo 2 mean? Mr. Sai Kumar is asking.
Sai Kumar. Sai Kumar. This is modulo 2. So what you are doing nowadays without saying anything is modulo 10. You don't say modulo 10, but you are doing everything modulo 10. So 9 plus 9 is how much? Or let us say 8 plus 7 is how much? So modulo 10 means 8 plus 7 is 15. 15 is 5 above 10. And this is place value. 10 to power 1 into 1, 10 to power 0 into 5. No, it is modulo 10. If you have the modulo 16, then you will have some method to represent 15. And this will be that last number. 0, 0 to or 0 to F is modulo 16. 0 to 9 is modulo 10. 0 to 1 is modulo 2. Is it okay? Shortest form. I cannot go more in detail into this. It's just arithmetic, modular arithmetic. You can go to algebra, linear algebra, and go for Galois field. I'm sorry. This is French name, Galois, Galois, Galois field. So you know set theory. Typical sets are fields if your elements are limited to some number and only some of the operations can be done on that, like that. Field, Galois field. No? So we are taking the Galois field kind of domain that way. This is type 2. I'm not taking this. I will do something for type 1 only. Before that, we'll go through modulo 2 polynomial arithmetic, algebra. So you have to multiply. You have to multiply this polynomial with this polynomial. So this 1 means repeated. X square means multiplied and x square repeated, right? And add it. So there is 0, 0 here, so they will appear. And what is x plus x? Modulo 2 addition. X plus x. X is any value out of 0, 1. So 0 plus 0 is 0. 1 plus 1 is 0. So x plus x is 0 always. Even if we have some power of x, this will still be 0. So x2 plus x2 will be 0. 3, 4 is there. So the multiplication is this, modulo 2. Division similarly that way. Only thing is there will be difference. So x minus x is always 0. Xn minus xn is also 0. We apply it here, right? So this is the way we divided this polynomial by x square plus 1. I'm going a little fast. This is the last 2 slides for characterization of LFSR. Application will take for 5 more minutes. So I'll finish in 2-3 minutes for characterization of LFSR, then take the 5-10 minutes for signature analysis quickly. So what I have, the type 1 LFSR, type 1 LFSR is this relation many to 1. Just remember this, what I'm doing. This is AM, which is summation of these two multiplication. If I write from 1, this will be C1 AM minus 1, C2 AM minus 2, C3 AM minus 3, and lastly Cn AM minus n. All added. The multiplication and addition all are modulo 2. This is conversion of connection of LFSR into a polynomial. I go back. Here, this is AM. I change my ink actually. Fine. This is AM here. This is A minus M here. What is the equation? This AM here is summation of all these taps. What is one tap? It is x multiplied by C1, x square multiplied by C2. This is xn minus 1 multiplied by Cn minus 1, xn multiplied by Cn. That's all. So AM is summation of all these step values. That is what we are writing here. Do you get it? This equation is peculiar to type 1 LFSR. That's all. And we have a generic polynomial for any sequence. We'll merge these two. That's all. So I start with Gx and replace this AM by the upper equation. Xm is here, the AM is replaced here by this. Is it okay? Is it okay? Now we segregate the variables. This is M variable, this is I variable. I can segregate the terms, 3 terms here, segregate them. So I take the terms of M inside, contain only M. I bring out the I terms outside. So I have this inside summation here. AM minus 1, Xm minus I. Right? This varies from 0 to infinity. 0 to infinity. And M minus I. If I open it up, right, from M0 to M, M0 to M, this will open up like this, or M minus 1, let us say. M here is 0 to infinity. I am taking M0 to M minus 1, and then next time M minus 1 to infinity. So you take 0 to M minus 1, or whatever, these will open out. And inside one, you will be left with M varying from M to infinity. M to infinity, whatever, or 0 to infinity, whatever. So we can change the variable there now. And that variable becomes, instead of M minus I, right, we have M minus I varying from M to infinity. So how M will vary? I varies, M minus I varies from M. I varies from 0 to infinity. That will be I0 varying from 0 to infinity. Right? Change of variable. You can do that. So out of this, we expand few things out, and rest of it becomes, because infinity is there. This is Gx. And this remains for me. And this is multiplied. Because maximum power is xi, and xi is already outside. This polynomial will be linear polynomial. Right? So that polynomial is, I'm repeating it itself. Gx comes out and goes here. Now, if it is taken to be Gx common, this will be 1, and this will be minus sigma Ci xi minus. But in modulo 2, minus and plus are same. So I will say 1 plus sigma. It's here. This I open up and see it here. This CIXI and some polynomial is here. This polynomial is typical to LFSR. This is characteristic polynomial. This is characteristic polynomial. If you expand this will expand up to only n, right? Because this is n. So that polynomial, which is 1 plus c1x, c2x square up to cnxn, is characteristic polynomial of LFSR. We call it Px. But this LFSR is peculiar. We'll take it from that part. So this LFSR corresponds to this polynomial. That's all. We have proven that the polynomial corresponding to LFSR is this one. This is a generic polynomial output sequence. I'm sorry. This is output sequence of this LFSR. But this remains common to everybody. Hence, this is LFSR polynomial, characteristic polynomial. That's a derivation. That's a derivation. If for initial state, every value is 0, you go back. This is your initial state. See it. This is your initial state. A minus I, A minus 1, up to A minus 1. Initial state. So your initial state will actually guide your output sequence. What initial state is? In general, we can take all zeros and last have to be 1 actually. Then this sequence will merge to 1 only, single 1. This here. This here. All zeros, only A and 1. In that case, we'll get this Gx to be 1 by Px. Right? The Gx is indicative of the typical LFSR. If your initial condition is all zeros and last 1, then this LFSR is unique and Px is there. Px is unique because we can change C1, C2, Cn. XOR gates we cannot, but we can change the connections. The C1, if it is 0, no connection. And C1 is there is a connection. If there is no C1, no connection. We'll keep going. And there is a connection. That's all. Right? And it also shows that with some more manipulation, little more manipulation, that if we expand 1 by Px, presuming there is a period P, so the infinity expression I can keep opening in the highest power of P minus 1. So the sequence gets repeated at output. It's the period of the sequence. So I can expand this and I find out that this sequence which I separated is actually available, evenly divides, right? So this Px can be divided by y minus xp, right? I'm sorry. Yeah, reverse way. Y minus xp divided by Px will give me this polynomial. This is a period. So this is doable and this has a period. So we can find out the period of LFSR from here. Finding out a P such that Px divides this polynomial. So P will be period of any LFSR if this polynomial 1 minus xp is perfectly divisible by Px. So choose a value of P in such a way that Px divides it. That becomes the P period error. If period has to be 2 to power m minus 1, then I can choose P to be 2 power m minus 1 here and prove that Px divides this polynomial. That's all, nothing else. So analysis is over. Analysis is over. Only thing is we have to keep track of some more transformation. So another transformation is same LFSR I can represent alternately. So can I say my AIT, right, is delayed. is delayed. Let us say xk delayed. So can I write AI in the form of time domain delay? If I put x to be 1 by y, can I write this? If I put x to be 1 by y or y to be 1 by x, if I put y to be 1 by x, can I write this now from this? This we have seen earlier, delay. We can interconvert. Can I write this? If I write this, right, then we go back to our LFSR, right, generating polynomial. LFSR polynomial, AM, we just compute again for that part. Equation 10.9. I don't know which was that 10.9. 10.9 is here. Yeah, this is LFSR equation. You put it here, that value. You put these values here, right, and get the polynomial. That polynomial coming out to be is this. This alternate polynomial for the same LFSR. I can interchange x and y just for representation here. So this will be equal to this one, xn plus c1 xn minus 1 plus c2 xn minus 2 cn x0 0. My earlier polynomial was 1 plus c1x c2x square cn xn 0, which is px. I get another px, which is px star or p star, which is this xn with coefficient 1, xn minus 1 with coefficient c1. We are changing, almost changing. So this is another polynomial, which is called p star. So each LFSR type 1 has two representations, p and p star, right? We just have finished the analysis of LFSR and we are going ahead, right? So if you take any example, can we go back or we can draw it anyway? So can you draw a LFSR corresponding to this? Right? It has flip-flops. This is one is coming here, tab, right? And this is x square, x cube. And this highest power. So we have one less there. And this x is coming up in summation. X is coming up in summation. This is connected. X square is also summation. So this is connected. And this, of course, has to be connected. So this is my C1, C2, and C3, right? C1, C2, C3, all are present that way. Now, for P star, we reverse our labeling for X only. We have labeled X, X square, X cube here. We'll do it reverse way. We'll say X3 is this, X2 is this, X is this, and 1 is this, right? And we have the same tapping, right? And we have only this one and these two taps, X and X square. X3 is not there or whatever, right? So we get that tapping. These two taps are there. The structure remains same. The first polynomial is this. With the same polynomial, the next kind of polynomial is this. You can obtain P star from P itself by putting X equal to 1 by X, which we can do now. Don't look at this figure. I'm doing something. Yeah, I'm doing this same thing. I have Px, 1 plus x, x square plus x cube. If I put x to be 1, replaced by 1 by x, right, my P star would be there. P star would be xn P1 by x. and that will be different, right? It's here. Same structure, two polynomials. If you convert this, I will get this. Fine, I can skip this type 2, you can take it up on your own. Periodicity is very easy. It says that few lemmas are there. It says that the period of LFSR has a period 2 to the power n minus 1. It is called maximal length sequence. And the polynomial of maximal length sequence is called primitive polynomial, right? And it also says that the P is reducible maximal length. P is reducible maximal length if your number of terms including 1 are odd. So if you have 1 plus x square and you have 1 plus x square only, the number of terms here are odd, number of terms here are even. So number of odd terms are necessary condition for a polynomial P to be maximal length. It's a necessary condition, not sufficient condition, right? Also, Px must divide 1 minus xp fully. Then this P will be period, maximal length period, right? And this P would be or 1 plus xk, whatever, 1 plus xp or 1 plus xk. The P would be 2 to the power n minus 1, maximal length. You can check for it, right? So this is the kind of demonstration. We have 36 taps. So for 3-stage LFSR, polynomials could be 1 and no of next tap duration. So we have power 3, power 1 and power 0, x cube, x and 1. For 20 taps, for 19 taps, we have x19, x6, x5, x and 1. This is a polynomial. So this is the listing of maximum length sequences. You can have anything. But if you choose these, you get the maximal length. 2 to the power 19 minus 1, period. The repetition period that way. Fine. Just last one, signal analyzer, maybe 5 minutes if I have, I don't know. Signal analyzer means compaction. So what I can do is, I can take LFSR, and feed some input serial fashion. So you have a circuit under test. You are getting some 1-bit output serial numbers. I am feeding it to LFSR and putting XOR here with AM. AM XOR with this. This is an LFSR. I take the output, right? If I do this, after I have a MSB here, LSB here. After the LSB is pushed in, I will get some pattern here and something out here. This I called residue. This I called quotient. The length of the sequence is M. Length of the LFSR is N, right? So Q will be of length N because I will get 1 bit out at every point that way. But residue will be of length N only. I can use this as a compactor. For M length sequence, I can take residue as a compacted or compressed form. So I have compacted my M length sequence to N length sequence. M length sequence to N length sequence, right? I have total 2m minus 1 sequences, which could be here, which are faulty sequences. Fault free is 1. I would have, right, same n for those different sequences, 2m minus n. And this is my probability of aliasing. which will be approximately 1 by 2 to the power n. If my LFSR is too large, n equal to 64, the probability of aliasing will be 1 by 2 to the power 64, very small. So this is a very good compactor. I take residue as compact, the kind of compacted one. If you do not have LFSR, you want to do theoretical analysis, you can do with polynomials. Without having pushing in this serial numbers practically, finding a residue and doing this, I can do the same thing theoretically by polynomials. Having a polynomial for this, having a polynomial for LFSR, and getting a polynomial out with division with a quotient and residue. What I mean to say, my input sequence would be Gx. My polynomial for LFSR will be P star. And this is equivalent to dividing polynomial, generating polynomial by P star that way. So P star is LFSR. It will divide the input sequence polynomial and will get Q here, quotient, and the remainder storing in LFSR. If I can do this polynomial division, my residue in LFSR will correspond to this polynomial R here. That's all, nothing else. Right? We are taking P star because we take the first bit as MSB. So the first point is not AM, it is A0 or AM something, and our n lies here. Right? It's a reverse polynomial, P star. The choice for, because in the complete sequence, my first bit is MSB. If my MSB comes later, I will choose P only here. Right? So I'll take just example and close. That's all. The example is he is giving some circuit. He is saying realize the LFSR with this, let the input sequence be this, and find out the compaction. The length of this sequence is how much? M equal to 8. What is the order of the LFSR? 5. So we are compacting the 8-bit length sequence into 5 bits. So I can say LFSR is there. My input sequence is this 1 1 1 1 0 1 0 1, and I will get a quotient which I don't bother. But what remains here as a residue after putting all these in this LFSR will be my compacted sequence. I take it as is. I take the polynomial for this Gx. I take this polynomial P star and do the polynomial division and find out the residue only. That's all. Right? This is given here. For P star, you have a habit of realizing the P, so you can convert P star into P xn and whatever we are getting here, P1 by x. So I get this. So we have one is here. No, one is here. Cn, whatever. C1 to Cn. And this is P star, so it is one to many, type 2. And my coefficients are I'm realizing C1 to Cn. So I will do this, tapping allowed that way, right? So my xn will be here and my 1 and x will be here. So 1 is necessary. I will take x. So this is there. This is not there. X5 has to be there. So this is already there. 1 is there. And this x4 is not there. I will choose those taps and realize my LFSR. This is this, my LFSR. Right? Realize with P star. P star. It is one to many, so it is type 2. Type 2. Now we take this LFSR and take corresponding polynomial division. Polynomial division. So my sequence can be converted, right? If I take this as or this as MSB or whatever. So possibly I'm taking this as MSB. So I'm taking the type 1 LFSR, whatever. So if this is LSB, this is 7, 6, 5, 4, and 3 is not there. 3 is not there, and 1 is not there. So 3 and 1 is not there. This is a polynomial. I take this polynomial and divide it with this P star X. And I will get this remainder here. That will what it would mean if I take this practically. This is a sequence. I push it in and do these computations practically. So this is my method 1 polynomial. This is method 2 bitwise. I take bit in. I keep doing XORing. I
Hello,
get
sir.
this insight. Yeah,
Good
yeah.
morning, sir.
Ah.
Sir, if you want, we can have a little bit break of 5 minutes if it is going to be a little bit long.
No, no, no. I think you should stop in favor of time of other speakers. My job is done. Just 2 minutes.
Okay, sir. Thank you so much.
Thank you. So if I do it practically, I will keep this pushing in to the LFSR and keep computing. And I'm responsible only for remainder here, so I'm not worried about this pattern. I will keep pointing out what is the pattern. Lastly, pattern is this with MSB here, right? Or last point here, MSB is this. So lastly, MSB is here. So this is one, whatever we have that 4 and 2 and 1 is not there. Fine. So the last bit will take this as a MSB that way. This is 4 is there, 2 is there, 3, 1 and x0 is not there, right? So we can repeat this process M1 and M2, first designing the LFSR. So step 1 is realize the LFSR. This one, step 1. Step 2 is you can do polynomial arithmetic. And step 3 is you do it digital circuit way of doing this M2, M1, M2, right? And verify that what you do polynomially is actually what LFSR is doing. So what we understand from here is this, we can actually compress M length sequential bit pattern into N bit pattern in the last, right? The same LFSR which is here can be used just in a typical mode as a random pattern generation, right? As a random pattern generation. I don't think I have it. So I will take the LFSR bit patterns and I will not have any input sequence, just connected this way. And there are taps here. I will take the output here. And naturally my output sequence for Q will have a period P, which will be maximal length period 2n minus 1. If I take the maximal length sequence LFSR, right? From the table, you can choose those taps for maximal length LFSR. Choose P star there and take some internal initial condition and see how it is generated. So you can write a Verilog code for this LFSR and see how the pattern is generated. Well, LFSR code for this is very easy. You write the 1 bit D flip flop, call them so many number of times, call XOR gates here for addition and connect it. That's all. Then you start with some initial pattern in the LFSR flip flops and observe the output Q. That will be the sequence length of P. It will repeat after that period P, right? And sometimes what has happened is I have a 1 bit sequence, I'm using one LFSR. I have another bit sequence, another circuit, I have another LFSR. So if I have so many circuits, I need so many LFSRs. Solution is just have one LFSR and bring these sequentially. Pattern 1, pattern 2 afterward, pattern 3 afterwards. And that becomes multiple input signature register. I have same LFSR, taking these bit patterns one by one. One bit pattern, once time. Second time, second bit pattern. Third time, third bit pattern. What I get finally is all bit patterns merged into a single signature. It's called multiple input single signature, MISR. That's all. Right. So we have done quite a initial brushing up with LFSR and signal compaction, which is so much required, and I should do it. So this is assignment 2 from my side. Given the polynomial of this, you realize the LFSR, type 2, type 3, type 1, type 2 both, and use it for compaction. I have given the solution, you can take it up, or book also has it. So this is the polynomial, we can presume initial condition or polynomial, and we can go ahead. Right? This is the division we get, some remainder we get. So I can actually share with you the solution also, but what you have to do is the assignment is put the code in Verilog. Or if you want, those who are not knowing the Verilog code, I will float the separate polynomial and realize the type 1, type 2 LFSR, take any generating polynomial and show that the remainder is actually equal to, remainder polynomial is equal to the bit pattern stored in the LFSR finally. Right? I will put that assignment in your canvas. Yeah, I'm sorry for overstepping the time. That's
Thank
all
you so much, sir,
from my
for
side.
your
Thank you.
very insightful talk. It was really very insightful for all the participants. They have enjoyed it, I believe. There were lots of questions from them, and some more questions are pending. So I request all the participants to actively participate like that. So the next speaker is with us, Mr. Tarun Goyal. Welcome, Mr. Tarun Goyal. A little bit brief about Mr. Tarun Goyal is like this. Mr. Tarun Goyal is serving as a principal engineer at NXP Semiconductors. He is bringing over 9 years of rich experience in SoC DFT design for testability domain. He holds more than 5 patents and has authored and presented more than 20 conference papers in both external and internal DFT events. Mr. Tarun is leading the industry's first 5 nanometer automotive processor system on chip DFT initiative. He holds master degree from MNIT Jaipur in embedded systems. So we welcome you, Mr. Tarun Goyal. Please share your screen and you can unmute yourself. We have made you panelist and you can start.
Thank you, Menkaj. Are you able to hear me?
Yeah, we can hear you. Yes.
Okay, I'm sharing my screen.
You can share the screen and you may start. So, Gaurav and Satveer, may I request you to switch the session, please? In meanwhile.
Okay, ma'am. Okay, ma'am. Just give us a 1 minute, ma'am. We will do that.
Okay. Okay. So Dr. Aditya, you asked some question why CN is equal to 1. So the answer is in the chat box. Professor Saula has replied in the chat box. CN is equal